Welcome to This Explainer. Today, we're diving into some massive AI news. We're looking at an incredibly exciting, entirely lexical framework that literally crushes automatic speech recognition hallucinations, and it does it without that heavy computational drag we're all so used to. If you build, use, or rely on speech-to-text systems, you know firsthand that transcription errors are an absolute nightmare. But there's a new paper out on arXiv by Mohammed Arif Jafadi Radani that proposes a brilliant solution. It drops word error rates significantly, and the best part? It does it with near-zero inference latency. Okay, let's kind of set the stage here by thinking about human linguistic errors. Imagine opening a dictionary and looking up the word error. You're going to find everything from a totally harmless clerical mistake, a simple slip of the pen, all the way to a fatal error, which is a severe, completely unrecoverable mistake. And honestly, the way we classify human errors perfectly mirrors the bizarre, totally wild phonetic hallucinations our machines make when transcribing speech. Sometimes it's just a minor slip-up, but often, especially when we're dealing with specialized niche terms, it is a complete, unrecoverable breakdown of meaning. So to break this all down, we'll be covering 6 key areas today. First, the hallucination problem, then limits of current fixes, followed by the error-aware solution, inside the math, results and performance, and lastly, exactly how you can go about upgrading your pipeline. All right, kicking things off with Section 1, the hallucination problem. So here's the deal. End-to-end automatic speech recognition, ASR systems, consistently hallucinate when it comes to rare entities and domain-specific terminology. It's a huge issue, and it becomes a complete disaster when the model's dealing with, say, environmental noise, heavy accent variations, or low-resource languages. Now, to fix this, developers usually turn to a technique called Retrieval-Augmented Generation, or RAG, as we usually call it. The whole idea is to feed large language models contextual documents so they can essentially go in and correct the ASR's mistakes. But as we're about to see, that strategy hits a very, very hard bottleneck. Which brings us to Section 2, limits of current fixes. Now, you might be wondering, why do existing RAG models fail here? I mean, why can't standard retrievers just catch these ASR misrecognitions and feed the right document to the language model? On paper, it seems like a super straightforward text search problem, right? Well, actually, not quite. This really gets to the heart of the dilemma we're facing. On one side of the ring, we've got standard sparse retrieval, things like your standard TF-ID. But this completely misses phonetic cues. Think about it. If a speaker says pneumonia, but the ASR hears pneumo-anya, standard text search isn't going to find that medical document. Why? Because the spelling is totally different. It completely ignores the phonetic reality of the mistake. Now, on the flip side, we have cross-modal embeddings. These try to map both the audio and the text into the exact same vector space to catch those phonetic similarities. Sounds great, right? But they carry massive computational overhead and sky-high inference latency. They are just way too slow for fast, real-time inference. And sure, you could use domain-specific knowledge graphs, but man, those require an absolute mountain of manual engineering. So what's the alternative? Let's get into Section 3, the error-aware solution. This is where it gets really interesting. Notice how the architecture breaks down into 2 beautifully lightweight core components that actually anticipate known misrecognitions before tokenization even happens. This is a purely lexical framework, relying on a single one-best ASR hypothesis. What that means in plain English is it doesn't need to generate like a dozen guesses and rank them. It literally just takes the top guess. First up, it uses a symmetric text normalization module. This aligns phonetic variants and standardizes the spelling before any tokenization occurs. And second, it uses this novel error-aware TF-IDF algorithm. It mathematically weights the retrieval step to anticipate the exact kind of mistakes the ASR is known to make. Let's look under the hood in Section 4, inside the math. Okay, so the absolutely crucial point here is that instead of heavy vector databases or those complex cross-attention embeddings we talked about, it uses a sparse diagonal penalty matrix. Let me break that down. Standard TF-IDF calculates how important a word is based on how often it pops up in a document versus the whole corpus, right? Well, this new method tweaks that score using historical ASR errors. It literally creates a matrix where the diagonal elements represent high-risk misrecognitions we've already seen. So during retrieval, this matrix applies a massive multiplicative boost to terms that match those historical error patterns. It basically yells at the retriever, hey, the ASR spelled it this weird way, but mathematically prioritized the documents that contain the actual, correctly spelled entity we know it meant. And because it's a sparse matrix, your computational footprint stays flat no matter how big your vocabulary gets. It only scales with the actual types of errors you observe. It's kind of brilliant. All right, let's talk numbers. Section 5, Results and Performance. When they actually evaluated this on the Persian subset of the FLEURS dataset, which, by the way, is a fantastic benchmark for low-resource languages, the results were just staggering. The error-aware hit rate surged from 53.7% to a massive 90.9%. And just to clarify, this hit rate measures the retriever's ability to actually pull up the document with the correct entity when it's fed hallucinated ASR output. It jumps this high simply because that penalty matrix directly neutralizes the phonetic mismatch problem we were discussing earlier. But wait, it gets even better. Let's look at the overall transcription quality. By just replacing standard TF-IDF with this error-aware variant, they dropped the end-to-end word error rate from 23.06% all the way down to 18.83%. I mean, that is a massive leap in accuracy for a system that adds practically zero inference latency. Because remember, that sparse matrix multiplication adds almost no compute time compared to running a standard vector database lookup. So, how can you use this? That brings us to Section 6, Upgrading your pipeline. If you want to grab these efficiency gains without, going through the headache of retraining your entire ASR model or your LLM, here is exactly how you integrate this into your existing architecture. Follow these 5 straightforward steps, and you completely avoid those complex N-best re-ranking pipelines, preserving your inference speed. Step 1, capture historical errors. Literally just log your ASR outputs against ground truth corrections during validation to build out your matrix. Step 2, swap the retriever. Out with the standard sparse search, in with this error-aware TF-IDF implementation. Step 3, apply symmetric text normalization. You just drop a layer between the ASR output and the retriever to handle those language-specific phonetic mappings. Step 4, maintain one best hypothesis processing. Stick with the top ASR guess. Don't waste your compute re-ranking a bunch of guesses. And finally, Step 5, monitor matrix drift. Because, vocabulary shifts over time, so just make sure to update your error logs automatically. To wrap this whole explainer up, I want you to chew on this quote from our analysis. The purely lexical approach trades semantic depth for inference speed. Look, while this sparse matrix approach is unbelievably fast and efficient, it doesn't and inherently can't understand the deep, nuanced contextual relationship between words the way those heavy cross-modal embeddings do. So, I'll leave you with this provocative thought. As we move into an AI future that demands both incredible nuance and lightning-fast speed, are these lightweight matrices going to completely replace cross-modal embeddings for error correction, or is a hybrid retriever ultimately inevitable? Think about how that might impact your own architecture. Thanks so much for joining me for this explainer, and keep building.